welcome to our correction of the first math midterm. Now let's take a look at the first question of exercise 4. We are looking for the limits of this expression, and in order to find it we need to understand the priority of limits. In this one, the elements that are going to be important for the limit are the two powers here, so we need to try to isolate them. Now that we have isolated those two, we find ourselves with two parentheses which are going to lean towards here -1 and here 1. Why? Because as we've seen in the previous exercises, this actually means the same thing as this. And that is actually going to lean towards 0. Now that we see that this is going to lean towards -1 and this towards 1, we find that expression. And now, using that expression, we use the rules of powers to deduct this expression, which allows us to say that the limit of this expression when going towards infinity is 0. Now we're going to take a look at the second question. In order to solve this limit, we must remind ourselves that this is actually equal to 1. So here we see that those two expressions are quite close, so we're going to try to reveal that part by changing this one a bit. We have changed the expression by putting x here and here, and we have made appear this term, which is equal to 1, so we can just replace that with 1. That leads us to having this expression. Then we know that x divided by square root of x is equal to square root of f. Therefore we have this expression, and the limit when x tends to go to 0 of square root of x is 0. So there you have it. Now for exercise 5, we are going to do the same as for exercise 3, which means that you're going to have to look at the subject before I actually start. So I'll let you do that and be right back. In this exercise, we're going to look at how to maximize the total revenue, noted TR. In order to do that, we try to express TR as a function of P and Q. And how to do that is just, we know that TR is equal to P times Q, so we just multiply the expression of P by Q, and we find this expression of TR. Then we're going to use the facts that we know about derivatives in order to solve the problem here. As we all know, the sign of the derivative of a function actually correlates to the variations of said function. So we're just going to try and analyze the derivative of this function, which we're going to call f, in order to find the variations. We need to find the derivative of f. Once we have done so, which leads us to here, we can just rearrange the terms to have them this way around. In order to find the signs of the derivative, we're going to use a technique which relies around us calculating the q's for which this expression will be equal to 0. This method relies around us calculating the determinant, which I put the formula of here. When we apply this formula to the expression we just found, b is going to be -1, a is going to be -half, and c is going to be 40. Then, when you compute the expression of the determinant, you'll have either one of three things happening. 1, the determinant is superior to 0, which means that we'll have two solutions for this expression being equal to 0. 2, the determinant will be equal to 0, which means that we'll have one solution to this expression being equal to 0. And lastly, the determinant being inferior to 0, which means that we'll have 0 solutions as to this expression being equal to 0. Once we have computed the expression of the determinant, we find that it's equal to 81, which means that we'll have two solutions. The expression of the two solutions are going to be those two. So once we have computed them, we find -10 and 8. And then, using everything we computed, we can graph this table, and that table lets us know the sign of f prime depending on q. Then, using that same table, we're going to be able to see the variations of f. I'm going to show you. Once we have put the arrows accordingly to the signs, we see that there are two possibilities for a maximal, which are going to be this point and this point. But what we know is that q cannot be negative, so therefore this is invalidated because it is negative. We see that it's behind the minus 10. So the only real solution for our maximal point is going to be 8 right here. So the solution is going to be 8. Now for exercise 6, we're going to be looking at saddle points. The first question will be, calculate those two and show that the only candidate for a local extremum is the point xy is equal to 30, 10. First, we'll compute those two. So how do we compute this and this? First, let's take a look at this. This is exactly the same as saying derivative of all of this, except you consider y as not a variable, but a fixed number. So you'll only derivate this according to x. And that leads us to having this. And then, for the second expression, it's the same as saying all of this derivative, except you consider x as a fixed number and not a variable. So we find this. In order to find what we call the saddle point, we need to fill two sets of conditions. The first one being that this and that need to be equal to 0. We are going to solve this by using a system of linear equations. In this system, we're going to plug in the two equations we had just found and put them in a way that puts on one side the variables and on one side the number. Once we have done that, we will multiply the upper equation by 3 and subtract it to this equation, because once we have done that, we'll eliminate the x and have a clear expression of what y is. So we just do it right there, and we find that y is equal to 10. Once we know that y is equal to 10, it is easy to say what x is equal to. We just do this quickly, and we find x being equal to 30. X being equal to 30 means that the couple that is going to be leading to a saddle point is 30, 10. Question A is finished. For question B, it's actually quite simple when you know what those three expressions mean. The first one means double derivative of f if you consider x as the only variable, and that leaves us with 1. Then for the second one, this means that we're going to do the double derivative of f considering that y is the only variable. For the last one, it's like doing double derivative of f whilst considering for the first derivative that x is the only variable, and for the second that y is the only variable. And that leaves us with a 3. And that's it for question B. Now for the question C, we're asked to conclude whether the function has its local minimum, maximum or saddle points at 30, 10. So in order to do that, we'll find another formula. We'll take a look at the second order conditions that I mentioned earlier. You're going to have to use this formula to find a number which is going to be either inferior, equal or superior to 0. Since we have computed mostly all of these terms, we can do it quite fast. Once we have computed the determinant, we find that it's equal to 1, which is superior to 0, and that this is also equal to 1, which is superior to 0. That means that the point that we just found is the local minimum of said function. And there we have it. Function f has its local minimum at the point that we found. That is exactly what we wanted, and that is the end of the midterm.
Allez, la bise en famille.